It's used a lot more for like calculus because like we have a few students that like come in to take that class and they can't make it. Oh, Obide's actually here. Okay. So Obide, no sign in needed. Just take this over here. Thanks for coming, Obide. I appreciate it. Here you are. So that's your handout. All right. So today we're gonna go over two sections. It'll be 7.1, 7.2, and there might be a modification to your cover sheet. Okay. So in terms of like maybe a few problems we can take off. It's just like at the very end. Okay, like one type of problem. But we're gonna go over 7.2. I think this is probably to me. I think it's like the toughest one to kind of understand or remember at least. I think it's easy to understand kind of when you're doing it, but it's kind of tough to just remember it. Okay, so that's why I'll definitely allow you to use cheat sheets, but make a lot of notes on your cheat sheet. Okay, so that way it'll help you on the test, right? Okay, so everyone, let's go over to your handout right here that I have here for you guys. This is actually just from your book. It's nothing different than what you have in your book. It's at the end of 7.2. And can you guys just tell me what you guys see right now? Like, what is this table saying? Like, why is there a table? Or what is it? What are we splitting up? What are we trying to explain? Like, what is this a table of? I don't know. What do you think, Natalie?
Different types of intersects, like different bisectors or lines.
Okay, yeah, we got different lines. We got different ways they intersect, right? So how many different types of lines do we have in a triangle, within a triangle?
There's 8 different definitions.
Oh, there's 8 kind of like different definitions, right? So we'll say this column is for like those lines kind of like meeting in the middle, okay? But let's just take a look at just the lines. So let's just take a look at these 4 lines, okay? So here's how you read this table. There are 4 different lines within a triangle. See that it's inside the triangle, okay? And then there's 4 different ways they intersect inside the middle, okay? But we're not here yet. Let's just take it step by step. Now let's look at these 4 types of different lines that are in the triangle, right? What differences or similarities can we say about any of these lines? Like, you can just tell me like, oh, I think this one does this or this one does this. What makes each of these different? What do you think? Oh, yeah, go ahead.
Altitude and perpendicular bisector both have a 90-degree angle.
Okay, so I love what you just said. It makes a 90-degree angle, right? But be careful of saying bisecting, because what does bisecting mean? Bisect. What does that mean when you bisect something? Like if I bisected this controller, what does that mean? You'd cut through it, and what'd you say? Cutting it in half, right? But if you look here, do you see it cutting it in 2 halves? Or do you see how this line goes from here to here? Does it cut this line segment on the bottom directly in half? It does not. So that's what an altitude is. It's like something that like goes from one corner of the triangle, goes to the other side, but does not bisect it. But it makes a 90-degree angle. Okay, that's an altitude. All right, that's an altitude. What about the other 3 though? What can we say about this? Like, oh, I got it. Can you see something that looks like the altitude? Which one looks like the altitude out of these other 3 lines? The angle bisector, the median, and the perpendicular bisector. Which one kind of looks like it the most? Yeah. Yeah, because like you said, it was 90 degrees, Natalie. Yeah, it's like between these 2, perpendicular bisector and the altitude. But they're still different. How are they different? Look closely at just these 2 designs here. What makes these 2 different?
They don't cut at the peak angle, kind of like at the top.
What do you mean, the peak angle? Like this one here does?
Like the bisector, if I cut, it like towards the right and not really towards like the angle at the top.
Oh, you're talking about like this angle at the top right here, right?
Yeah, it wouldn't cut through like that.
Do you know what that's called? Like the corner of like the corner angle thing of a triangle? It starts with a V. What do you think it might be called? Just take a guess. It's like a math term that you've heard before. Yeah. Wow. You guys are really good. Yeah, these are vertexes, or you call these vertices, okay? Like plural. Each of these are vertices, okay? Does the altitude come from a vertice? Does it actually stem from a vertice? Does it come out of a vertice? Does it come away from out of one of these corners? Yes. You see this corner here? That's an altitude. So it does come from a vertice. Does a perpendicular bisector need to come from a vertice, though? It does not. Okay? So if you want to make a note to yourself, say that the altitude comes from a vertice, the perpendicular bisector does not. But it still makes 90 degrees, okay? So that's how these two are similar. They both make 90 degrees, but one comes from a vertice and one does not come from a vertice. That's the up here. And then one does. There's also one more difference in the perpendicular bisector. Notice that I emphasize bisector. What is different between the perpendicular bisector and the altitude? Yeah, David?
The both cuts on the perpendicular bisector are congruent, or they're
No, you got it. You got it. Yeah. So once you guys are finished writing, I want you guys to see what David kind of figured out. It's kind of cool. I would say these two are like the biggest ones to like try to figure out what's different. So again, they're similar because they make 90 degrees, but the perpendicular bisector does not come from a corner or vertice, whereas the altitude does. And earlier we said that when you hear bisector, it cuts in half, right? Notice perpendicular bisector actually does cut it in half, the side. Do you see like it comes from one side to the other? It cuts the other side in half, right? Does the altitude do that? Does it cut the other side in half, this side here? Did it cut it directly in half into two equal parts? It does not, okay? So main differences here, perpendicular bisector bisects the other segment in half into two equal parts, and it does not come from a vertice. The altitude does, okay? That leaves us with two other ones. Let's try to figure it out. What is an angle bisector and a median? Like, how would you describe what they are? Like, look at, yeah, what do you think?
Like an angle bisector is something that bisects an angle.
Yeah, like this here. Like, do you guys see this angle over here? Right? If I want to make an angle you don't have to draw it, but if I had to make an angle bisector, the only thing I have to do is I have to make a line that cuts this angle in half. Does that make sense? And it doesn't really matter where it ends up, okay? Same here in this corner, and it does start from a vertice, okay? So 3 of these lines start from a vertice. Angle bisector, median, and an altitude all start from a vertice, okay? Same with the median here. So an angle bisector just has to cut the angle in half that it's coming from, right? Boom. If I had to draw another angle bisector, I just have to cut this angle in half. Okay. By the way, you notice I made 3 angle bisectors? Did they meet at a point, by the way? Yeah. Oh, you see that, right? And they meet at a point. If you are paying attention to the right side of the table, that point that I just made is actually called the incenter, okay? So that's what these lines are, okay? These lines are like if 3 perpendicular bisectors met, if 3 angle bisectors met, if 3 medians met, and 3 altitudes met, okay? They have different names, like the one, if all 3 angle bisectors met at like a singular point, that's called the incenter, whereas the perpendicular bisector, if all 3 of them met, it's called a circumcenter. We're not that far yet, okay? I'm just giving you a preview, right? Like each one, if they have all different names, like the point they meet at and like the actual lines themselves that are called different things, okay? All right, one more thing. What is a median now? What do you think that it does? How would you describe a median? It's the last type of line that's different. This one cuts an angle in half. Okay, angle bisector cuts an angle in half. Okay, but what does a median do? It does not cut a angle in half, but notice what it does do. Does it come from a vertice? This line? It does, right? It comes from a vertice to the other side. What did you notice it does to this other side? Yeah, it cuts it into what? 2 equal sides. That's a median, okay? So all a median does is it goes from a corner and it cuts the other side in half. Does it make a 90-degree angle though? Does it make a perfect 90-degree angle? It does not. So that's why it's different from the perpendicular bisector. Okay, some people are like, oh, that looks about the same, Mr. Wee, but it's like, no, the median comes from a corner and actually cuts the other line in half. Okay, perpendicular bisector also cuts the other line in half, but it makes a 90-degree angle and does not come from a vertice. Okay, a lot to take in, huh? That was a lot, but I just want to summarize it so that way when we go through it, you're like, oh yeah, I think I saw that in the beginning of class. Okay. All right, so remember, this is called the summary sheet. So this first page is just a summary. When you turn to the next page has them all way in more detail, okay? So like each definition, like the first one's like perpendicular bisector. It'll go through what exactly that is. Then it'll tell you what a circumcenter is. Then I'll tell you what an angle bisector is. It goes step by step to describe each one, okay? Whereas this sheet over here in the very front just gives you a summary of everything, okay? Okay, so I need to get a book really quick. Anybody else bring their book with them at all?
Yeah.
Oh, you did? Okay, so we might use it just for like the very end to look at some problems we can skip. Okay, but that's all I need for you guys to have. Like the only reason why you guys should have the book. But I don't normally require you guys to bring it at all. I just wanted to know if anyone happened to have it. Okay. All right, so now we're actually going to do some problems. We're going to go through some stuff with this knowledge, okay? All right. So theorem 1. Sorry, just give me some time here. So we've got your theorem 1, example 1C. Okay. So let's go through an example now. This is going to be 7-1. And the first thing we're going to learn about is bisectors of triangles. So in this first chapter, I think you're only going to learn of 2 different lines that we just talked about, okay? Okay, so we're going to learn about, in this chapter, the 2 things that we're going to learn are these 2, these first 2, okay? So this is 7.1 for perpendicular. So if you want to write the section name, this is 7.1, this is 7.1. These 2 lines are going to be covered, and their centers are going to be covered as well, okay? And down here, it's just going to be 7.2. I would say these 2 are harder to understand. Okay, so let's go through this now. So let's see, okay, so here let's talk about using the perpendicular bisector theorem. Sorry, it's kind of weirdly spelled, but using perpendicular bisector theorem, okay? Theorem. I'm sorry. You don't have to spell it correctly, but in case you want to know, okay? It's going to be the first little subtopic within our section. And here's your example. It's going to ask you to find each measure. And in this case, the measure that you're going to find is this thing called RT. And let me draw you the triangle that you're going to solve for, okay? It's going to look like this. Here's a triangle. And here is a line. This is the line RT, okay? It's going to make a perpendicular line. And then this is going to be 2x plus 3, 4x minus 7. And I want you to find RT. How long is RT? Oh, sorry. So I messed up on some labeling. Mr. Wee, what's wrong?
Yeah, Mr. Wee.
Yeah, what's up, Mr. Wee? Come on, Mr. Wee. Get it right, Mr. Wee. This T is not a T. This is not a T. Okay, so let me show you what RT looks like. Okay, so this is RS, Mr. Wee. Okay, and these 2 lines over here, this is Q and this is T. Okay. So in the corner over here is S. This point is T and this point is Q. Right. Okay, so if you don't know what a perpendicular bisector is, or there is a perpendicular bisector in here, okay? Does anybody know what line is the perpendicular bisector? So if we need to know by definition, this is in your handout. A perpendicular bisector. If a point is on a perpendicular bisector, then it is equidistant on the points, the endpoints. All you basically need to know is here's a line that goes straight down. That's a perpendicular bisector. It makes 90 degrees, and then it cuts the other side in half. Okay. So judging by this here, does anybody see where the perpendicular bisector is? Where is it? Where is the perpendicular bisector? What is the line that makes the perpendicular bisector? Yeah?
RS.
Does everybody see RS? Okay. So that means it makes these two lines equal. Also, if you want to read very closely, if you want to know why, so if a point is on a perpendicular bisector on the segment, then it's equidistant from the endpoint of the segment. So here's a perpendicular bisector. There's a point here, okay? These two lines are also going to be equal to each other as well, okay? So for a perpendicular bisector, once it cuts in half, it cuts this line in half and it also makes the other two lines equal to each other, okay? That's what's cool about perpendicular bisectors. Okay, so what do we need to do now at this point? If I know that both those sides are equal and I need to solve for RT, what am I going to do now? What should be my first step? Yeah? Anybody else want to try this? No? No? Okay, yeah. What do you think, David?
You can put 2x plus 3 equals 4x minus 7 and solve for x.
How did you know that?
Because they're both equal.
Which things are equal? What
Both
things?
One, RQ and RT.
Okay, so RQ is equal to RT. And RQ is 2x plus 3. We could just substitute RQ for 2x plus 3 and RT for 4x minus 7. Minus 7, I'm sorry. That's minus 7. I wrote that incorrectly. And then now we just solve for x. So we subtract 3 from both sides. So we get, actually, I don't know if 3 would be the... Yeah, you know what? Actually, let's go back a second. I think I just made it confusing. Let's not do minus 3. Let's do this. Why don't we add 7 to both sides? Yeah, that'd be better. You could have done what I just did too, like subtract 3 from both sides, but I'll let you know from experience it'll take a little bit longer to solve, okay? So now we have 2x plus 10 is equal to 4x. Now what do we do?
Subtract 2x.
Uh-huh. And then now we have 10x is equal to 2x. Now what?
Fine.
Both sides by 2. And then that'll give us x is equal to. Are we finished? Third question. Because is it asking for x or is it asking for something else?
Asking for RT.
It's asking for RT. So RT, if you look at it, is 4x minus 7. What do you suppose we do now to solve for RT? We have solved for x now, but what do we do with x? What do you think, Alina? Yes, because you know what 5 is, we can plug it back into 4x minus 7. So RT, again, just to reiterate, RT is equal to 4x minus 7. And you simply substitute in 5 for x, and then you should get 20 minus 7, and then RT is equal to 13. Okay, there you go. Let's see here. Would you guys like to try one? Okay, so why don't you guys all work on the big whiteboard now, since we have enough people, enough room now. Okay, why don't you guys try this problem here? It's the same thing. Okay, it's the same type of problem, but here it is. Here we are. Oh, let me get you the whiteboards and stuff, the whiteboard markers. Okay. So, you see it. Oh, I'm supposed to be the one that has it.
I have a Sharpie.
No. No, I'm good. Thank you. Oh, there. Okay.
From
Alright. Here you guys are. So you guys can grab it. Just remember, please don't ever squeeze down and stuff. Okay? You guys can grab some erasers. And then by the end of class, just return. But right now, you can. So, someone besides David, where is the perpendicular bisector? Does anybody see it? What line?
SQ.
Yeah, you got it. There you go. Yeah, that's good. If it's a perpendicular bisector, which lines are equal? Which lines are now equal to each other if it's a perpendicular bisector? Does anybody see which lines are equal? Oh, it looks like Natalie, you have it. So you said 3x minus 1 is equal to 5x minus 3. Which lines are equal, though, when you do that?
P, Q,
Oh,
and Q.
Something? Sorry, I blocked the letter, right? What else? There's two more other lines that are actually equal to each other, too.
P and S and blank.
Yeah, S and blank. Yeah, there you are. Yeah. That's very, very good. Okay, good job. Don't forget, you're not solving just for x, but you're solving for PQ. Yeah, there is. I'm sorry, it's an R. That's an R. Yeah, I just blocked it. So let me see what you guys got. Okay, so you subtracted 5 x plus x. Oh, what you want to do is you want to get all the numbers on one side. So you subtracted 3. You should have subtracted 1.
Oh.
Or added 1. As a leading mistake. Added 1. Plus 1. 2x, negative 2x is equal to negative 2x.
Oh, that's plus 1.
So that'll be x equals negative 2. So yeah, x is equal to negative 2. And then, so now you found x.
We plug it in
So where though?
to the equation.
Which equation? Yeah. Yeah, there you go.
So 3 times negative 2 plus 1. So that'd be negative 5.
No, you're right. It's 3 times negative 2 is.
Negative 6 plus 1, negative 5.
Yeah, because the answer actually was 7. No, you're right. You're right. Let's see. Oh, that's why. Because you guys mixed it up. It's 3x plus 1. back in your original equation.
Oh,
It's 3x plus 1, and then it's 5x minus 3.
okay. 5x minus 3.
Uh-huh.
So I'd add 5. No, what's the close back by that? Yeah, let's do it all over again. I don't want to like fill in things.
Uh-huh.
So, oh, I just close.
Add 3 to both. Oh, no, just add 3, not 3x.
Oh.
So they just choosing cereals. Yeah.
So get rid of 3x plus 4 equals 5x. Subtract and get 5x on both sides. So that'll be here.
Yeah, so we don't want that.
Minus 3.
There you go.
4 equals 2x. Divided by 11, so x equals 2. That would be x equals 2.
Yeah, there you go. Now plug in back in column 2.
So we said
There you go. You guys got it. Okay. Very good. Okay. So actually stay up there really quick. Okay. Now both you guys, what I want you guys to do now is, let's see. Where's my, I'll take it. All right. We're all going to do this together, but we're all going to have different shapes. I just want you to make a big triangle. Not huge, but like about this big. Okay. I want you to make a big triangle right now. So actually, you know what? I'm gonna do this on the separate piece of paper. So that's very good. So for the people that couldn't make it, they can see what I'm doing. Okay, so actually, I'll be doing this on the projector. Okay, but same idea. I want you to draw a big triangle. No matter, it doesn't have to be isosceles. It could be anything you want. Okay, big triangle. Right now, what I want you to do now, it's very hard to do. Okay, but what we're gonna do is on every side, we're gonna make a perpendicular. Oops. Well, you're gonna make a perpendicular bisector. I want to see if this helps to understand. So what you're gonna do is you're gonna find each side. I'm gonna make a perpendicular bisector, and don't be scared because it might not look like the ones that we saw in the book. So find the midpoint of one of the sides. Any side. So yeah, the midpoint. So I just do the midpoint. All right, so I'd say the bottom one's the easiest, okay? Now, watch me first, okay? Watch me first. I'm going to make a perpendicular bisector. So this means that it bisects this line, right? But does it have to hit the vertice? Go in your definitions or go in your segment. Does it have to get into the corner, the perpendicular bisector? Look very closely. Take a look at your picture. Does it have to come from the vertice? It does not, right? Your picture should have looked like, I mean, the second page looks like it has to come from a corner, but let's look very closely here. This is an example of a perpendicular bisector does not come from a corner. If you're an altitude, you do have to come from the corner. But if you're a perpendicular bisector, you don't. So watch. When I draw mine, I have to draw this line so it's 90°. It makes a 90° angle. So watch. Shoot. Did it actually touch the corner? No. It did not. So that's what I want you guys to do. I want you guys to make a straight line from each segment from the midpoint. And I want you to make 90°. So make it go 90°. So this is 90°. This is 90°. And then I think, let's see if I can get this one right. Alina, very smart. You're using a straight. Okay. Oh, bad. Oh, by not bad. You're doing it by eye. That's good. That's really good. So David, you have a good one too. Right. So hold on, Alina, make sure that line makes a 90-degree angle. So let's see. 90 degrees would look like this. You see your report? Make it. Oh, was that what you did? So that's through the middle, that's the midpoint, right? So now draw. Oh, so you yeah. Right there. Okay, go. The other one here, so this has to be 90 degrees. So that's about 90 degrees back. Stop right there.
So
Looks good, huh? Okay. Good. Okay, so you guys see how it meets in the middle somewhere? It doesn't meet directly in the middle, but it meets somewhere in a midpoint, right? Okay, cool. All right, you just made a circumcenter. Okay, so make it down here. You guys are excited about this. Now, what I want you to do is keep that midpoint. So make a really strong dot. Okay. I want you guys to erase the other one and keep that down. I know you're like, wait, Mr. Lee, what'd you do this? Oh, come on, Mr. Lee. Come on. I know, but there's a whole point to this.
No, that's good.
Okay, so go ahead. Just keep the midpoint, right? Okay, so for the people at home, we are erasing these lines and then making a center. So I told everyone to draw a center here. Boom. Right there, okay? There's a center. And if you could erase these lines, this center would be called the circumcenter. Okay. Hey, Vivian. Sorry, I'm just having an extra class for another class. Okay. Oh, thank you so much.
yeah,
That's awesome.
see you later.
Thank you. You're awesome. Thank you so much.
I have my moments.
Oh, you're always cool. Thank you. Okay, so now, hold on, guys. You're not finished. Now, I know it's confusing with my drawing, but it's a lot easier for you guys, okay? Draw, you see from each vertice now? If you guys can, I'm doing it in a different colored pen. Let's see if I have a different colored pen on me. Shoot, I should have another color. Okay, I'm going to do it in red. I want you to, from each vertice now, to connect, so from each corner now, to connect to the actual circumcenter that you just drew. Don't worry, it doesn't have to make 90-degree angles. From each corner, draw a line to the circumcenter. Just from the corners. Yep, you got it, from the corners. This does not have to make a 90-degree angle, just as long as it connects to. It's okay. Yeah, you can freehand it. Just keep it that way. Oh, don't lose the center. Okay. Hold on, David. I don't want you to keep just this, okay? There you go. Okay. And David, when you guys are finished, I want you guys to analyze. What do you notice about the lengths of these sides? No, it's okay. No, that's it. That's it. I only asked you to make it from the corners. Now, what do you notice about these three side lengths? So if we go back now, look at mine. Mine's not that great looking. Okay, so let's go back to your seats now and let's look at bask in your glory. Okay, bask in the glory. I want you to have a quick look at the circumcenter. This is called the circumcenter. And take a look at that definition right there. I mean, this is a summary, but there's a really, really in-depth. Actually, yeah, let's look at the in-depth one. Let's go to the second page. This is the circumcenter, and this tells you by definition what a circumcenter is, okay? Perpendicular bisectors of a triangle intersect at a point called the circumcenter. Sorry, you might not be able to see. That is equidistant from the vertices of the triangle. What does that mean? You guys, Alina actually just kind of explained it, but what does it mean? So in our language, what are we talking about here? The perpendicular bisectors intersect at a point. right here in the middle. Okay, get it? It intersects at a point right there. That's where it intersects, right? Here are the perpendicular bisectors, if you guys can't see it. I'm going to draw in purple. You guys see that? You guys did this too, right? There's a perpendicular bisector. There's a perpendicular bisector. It met at a point, right? But look at the black lines, though. Where did the black lines come from? Where did the black lines come from? These ones right here. Boom, boom, and boom. Where did these come from? They came from... Wait, you guys drew them, too. You guys drew the black lines, too. What are they called? Yeah? Yeah, the vertices. Boom, boom, and boom. And then what did you say about these line segments, Alina? The ones from the vertices when you drew them there. They're equal. So guess what? I know it's hard to see because I wrote all over it, but this point right here, PA, PA, that's the center, P to A is equal to P to C and P to B. So that means all those lines that came from the corners now touching the circumcenter are equal. Does that make sense? Just like you guys right here, if I had to recreate it on yours, I'm going to go with Alina's Natalie. Let's call this P, and then let's call this A, let's call this B, let's call this C. I drew the circumcenter, right? So if I drew lines from the corners now, wouldn't you say they're equal? PA is equal to who? Who would you say PA is equal to?
PB.
PB, and what else is equal to also?
PC.
PC. Does that make sense? When I make a circumcenter and I connect the dots to the corners, all those segments in the corners are equal. That's the circumcenter. So that's what that theory is saying right there. Okay? At the very end it says, they intersect at a point called the circumcenter and is equidistant from the vertices. Okay? So what is this going to look like on, a question or something that I might ask you to solve? And by the way, if you can think about it, how would this help in real life? Who would actually need to know a lot about like triangles or something? What do you think?
People who are making gardens. I don't know.
Gardens, yeah. What if someone made like a very specific triangle and they wanted to put like a fountain right in the middle where it's equal from all corners. So that way everybody in every corner can access the fountain, the circumcenter equally, right? You have to know a lot about shapes. So basically people that are architects, they kind of got to know a little bit about math, okay? So that's one way you can kind of think about it, okay? Like a person that makes gardens or architecture. Okay, anyways, let's give you a challenge problem with that in mind, okay? So let's see. 7.3. 3 here. That was a 7.3. That wasn't too bad. No. Where's a good one here? Where'd be a nice one here? I'm sorry, I thought I had a pretty challenging problem, but that's basically all I guess I wanted you guys to know. It wasn't that bad, was it? Okay, yeah, I guess that's it. That's not too bad for that. Okay, all right. One more thing now we're gonna learn in this section is called the angle bisectors. So we're gonna move on. So that's it. That's the circumcenter. That's all you need to know. Okay. Once you find the circumcenter, it's pretty straightforward. Okay. But now we got to learn about angle bisectors. What does this mean? Angle bisectors, okay? So this one I'm just going to explain briefly, really quick. That's an angle bisector right there. Just goes from the corner and it goes to the other side. Doesn't matter what it does to the other side. Doesn't make any 90-degree angle. Doesn't make two equal sides. It just cuts the angle in half, okay? Let's take a look at, let's say, this now. Here's another angle bisector. Oh, sorry. Can't get it to really properly align here. Okay. So here's what happened here. If a point on the bisector of an angle, where's the angle bisector? Can everybody see that? Can everybody see the angle? Where's the angle? Can you point it with your finger? Where's the angle? Right in the corner right here, right? So what's bisecting it? What's cutting that angle in half? Which line is cutting that angle in half?
I can't really tell, but it's maybe F.
F connected to who? That's a point. Point F is connected to who? That's very good, but where's it connected to?
Point B.
So we call that BF.
Okay.
You're right. Okay, so BF. In fact, you see how BF goes from B to F, and it just keeps going as an arrow. Look at the way they drew BF. It's like starts from a point, and then they draw this to an arrow at the very end. Whoa! I just drew in the book. Whoops, that's not good. Okay. Anyways, that's BF. Okay, so it bisected that angle, and then we just picked any point on here on the bisector, like right here. Okay. What do you notice about these two sides? So let's say I made that point here. Let's see how far it is from this side to this side. What do you notice about the lengths of these two sides? DF and FE.
They both have 90-degree angles.
They both make 90-degree angles. And what else?
They're the same measure.
They're the same measure because look here. I know it's hard to tell, but if BF bisects this line here, or bisects this angle, okay, then it makes two things that are perpendicular, FD and BD, and they're actually equal to each other as well, okay? If a point is on the bisector, so F is on the bisector right there, then it is equal to the sides of the angle. So here's the angle, this big angle. These two sides make the angle. I picked a point on the bisector, and then that point is equally distant from this side and this side. Does that make sense? So if I looked at this problem here, how would you solve for SP? Sorry, this is S. S is right here, and then this is P. That's SP. We have to solve for that line. Yeah.
You could put 6x minus 7 equal to 90. Solve.
Okay, so why don't we just draw this as a note right now? Okay, so let's say for this is so let's back up a second here. We're gonna make this a quick note, okay? So this is still on 7-1. This is using the angle bisector theorem. Okay. Here's an example. So if you had, so just create a big angle like this, like that, okay? Let's create an angle. And then let's make a perfect line that bisects this angle in half. Like that. I didn't do a great job, but there we are, okay? Someone tell me where they want to make a point. Where? Tell me when to stop.
There.
Right here? Okay, right there. Okay, we're going to call that point S. We're going to call, let's see. This point's going to be P. It's going to be perpendicular like this. It's going to make a 90-degree angle, okay? And then try to draw the same point on here. So like you see how from the corner here I drew to P? From this corner here, try to draw the same distance here. Like I would say P is about like this far on this side, okay? And it makes about 90-degree angles, I think, if I drew that correctly. And then this is J and this is M. So again, what could you say about, here's the angle and here's the angle bisector. What can you say about these 2 points here? These two lines, SM and SP. What can you say about these two lines here? The way they're drawn. Yeah, Alita? They're equal. SP is equal to SM. And let me draw you one more thing. If SM is 3x plus 5 and SP is 6x minus 7, how would you solve for SP? I want you to find. So the question I was asking was find the measure for SP. What do you suggest I do now to solve for this?
same thing we did there.
Which is what though? What does that mean?
3x plus 5 equals 6x.
Why would you set 3x plus 5 is equal to 6x plus minus 7? That's a good question. No, I mean, that's good. That's correct, Obai, but why did you set them equal to each other?
Fine, that's just how you.
Well, it's not. You don't want to just say it's just how you do that, but why? Why is it that you set 3x plus 5 is equal to 6x minus 7? Yeah, Natalie?
They look the same measure on each of the lines.
So SM is what measure? It's what?
90 degrees.
Oh, it's not 90 degrees, but it's right here.
3x minus 5.
So that's why in place of SM, I can put 3x minus, or 3x plus 5, okay? And then what is SP equal to?
6x minus 7.
That's why we set them equal to each other, right? Because we know SM is equal to SP. Mathematically, we could just substitute it for the actual values. Now let's solve for x. We add 7 to both sides to get rid of, we put the numbers on one side and then we put the x's on the other side, okay? So now we have 6x is equal to 3x plus 12, okay? And then we subtract 3x from both sides. Now we have 3x is equal to 12. And we divide both sides by 3, I'm sorry. And x is equal to 4. So go ahead and write these steps down. You have solved for x equals 4. Now I must ask if we're finished once we figure out x equals 4. Why do you say no?
Yeah, plug it
To where specifically though? By
in. SP.
SP, which is what?
6x.
So because SP is equal to 6x minus 7, we're going to plug in x 6 times 4 minus 7, which is 24 minus 7 would be, what is 24 minus 7? What would that be?
6.
17.
Very good. Yeah, it was very good from all you guys. Okay, but I saw Alina being very, very nice and very considerate. Like, "It's 17." But I just want to make it a big deal. Okay, it is 17. You were correct. You guys were too. Okay, SP is equal to 17. Just a trivia question here. What if I plugged in x is equal to 4 to the other question or to the other side?
You get SM.
You get SM. That's correct. This is SM. But what would be the number? You don't even have to do the math. How did you know it's 17? Because they're equal. I mean, you could check. If you wanted to make sure, you could plug it in, just see if it's equal to 17. If it is, you did it right, okay? Because the whole point is, yes, they're supposed to be equal, right? So what you just did basically was just like, you found a value that made the both sides equal. So if you found the right value, you plug it back in, they should be equal, okay? So that's why we said equal to each other. We found a value that made both sides equal to each other, okay? All right, so we're done with that now. Let's move on to 7-2, and we'll call it a day. Okay, so it's more lines. So we just figured out this and this. We just played them. By the way, that. Oh, I guess I didn't talk about that, but this is the only thing I'm not going to go over for 7-1. You need to go back and learn what an incenter is. It's not as bad as you think. Okay, incenter, right? Just go ahead and try to understand what this is, and then see what the math is for this one. Okay, that's like example number 3 or 4, I think. Yeah, it's example number 4. Okay, so if you need to write that down, it's example number 4 in 7-1. What kind of math you need to know for the incenter. Okay. Next up, we're going to do the median and the altitude, and then we're going to find the centers. We're going to check out the centers in there. Okay. So let's see. What are we going to do for 7-2? What do I have planned for you guys today? Okay. Active Inspire. Oh, yes. All right. I believe this is the one. All right. So let's see here. Okay. So let's go back on the board. Erase those triangles now. Okay. I want you to erase those triangles. We're going to draw a median. We're going to draw medians now. So create another big triangle. Okay. So at this point, I'm going to draw a random triangle like this, okay? Your triangle might not even look the same, so don't worry, okay? Now, watch how I draw the median. I want you to draw medians on all sides of the triangle, so hold on. You can look at your definitions now. If you're comfortable doing it, you can go ahead. But here's my median, okay? Midpoint here. That's a median. Now, here's what you're going to have to do. You need to discuss with your partner or your neighbors. Actually, no partner, just everybody right now. Discuss with each other. How the heck am I constructing a median? What is a median? Okay. Very good. Very good.
Do you draw the same tick marks?
Huh?
Can we draw the same tick marks?
You can. You can. I'm just trying to give you a clue of what a median is doing. What is a median doing? It comes from a corner. You guys got that. But what does it do to the other side? Ah, so Ovide's got the idea. I see that. It goes from the corner and hits the midpoint of the other side. Very good, guys. All right. Looks good. Okay. Now, look at your triangle. You can look at mine the way I look at this, okay? Now, go ahead and pick the left median right here, whatever your left corner median is right here, okay? And I want you, this is actually, this center for medians, what's it called? It's called a centroid. So in the middle here is the centroid. You don't have to draw this. Don't write this down. This is called the centroid. I'm just saying that's the centroid in the middle right there, okay? I want you guys to look at this no matter what triangle that you have. Obide's, David's, your guys', mine. Let's look at this line here. How does the size of this line compare to the size of this line? Even though they're on the same line, but they're separated by the centroid. What would you say about the size between this and this, roughly?
One bigger, one smaller.
By how many times does it look like?
Two.
By 2 times. How about this one? Could you say the same thing about this? How about this? Here's this side and this side here. And how about this length here? Look at your triangle. Does it follow the same thing? So this pattern, okay, does it only happen on my triangle? Did this pattern? No, it happened on everyone's triangle. So the whole point is, no matter what triangle you have, if you draw all the medians, okay, in that triangle, they all meet at that point, and you connect the lines here, okay, one side's always going to be twice as big as the other one, okay? Or you can look at it like this. You guys ready for this? Let's say that this is A, B, C, okay? You know that AB is 2 times bigger than AC, right? Right? That's what you're saying. AB is twice as big as BC. Oh, BC, right? BC, okay? So another way you can look at it is this. This is all AC. This is the hard part to understand, okay? AC is also equal to, it's like this. It's like saying AC is equal to how would I say this? Or let me see. In comparison to AC, let me see. AB is, you could say, 2/3 the size of AC. Does that make sense? I don't know if that makes sense. Yeah. It's like you cut this into thirds, okay? Like AC into like 1, 2, 3 parts. AB, if you look at AB, that's 2/3 of AC. And then you could look at BC as, what would that be to AC? That'd be a tough one. Huh? Sorry. So I'm so sorry about this, okay? So you can look at it like this. Let's look at all of AC, okay? If you said AB was twice as big as BC, then you could also say AB is like 2/3 the size of the whole line, okay? I know it's a little hard to see that, right? But just trust me on this, okay? What about BC, though? What would you say that is? Say it. 1/3, okay? How about over here? What about from, well, what if we, give me some letters here.
D. E.
And we'll just stop, okay? Let's look at, now let's go ahead and look at a separate stuff, or separate set of stuff. What's this whole big line called? From here to here, what do we call that? We'll call it ED, okay? BE is what times ED? Uh-huh. And then how about, what is this one called? B what? What about BD? How does BD compare to the big one? You guys pretty much got this down, right? Now have a seat now and look at your definitions. If you looked at this now, would this make sense to you now? Look very closely at the definitions and see if it means the same thing. So what you drew again, you drew 3 medians, boom to boom here, right? Then you drew another median, right? Then you drew another median. They all met here, okay? So let's look at BL, right? BL, how does BP compare to BL? The whole line. BP compared to BL. BP would be equal to what? So BL, and you created 3 medians. And they hit this thing called the centroid. Okay, that's the middle dot there. How would BP compare to BL, the whole thing? Hey guys, do you guys see this written anywhere else in this definition? Right here. So now do you see how this makes sense a little bit more, okay? So let's read what the actual definition says. The medians of a triangle intersect at a point called the centroid. That is 2/3 the distance from each vertex. So basically, it's just doing this. It cuts it into one side that's 2/3 and the other side is 1/3, okay? It does this for all the other lines. Does that make sense? That's it. That's a centroid, okay? Let's work on one problem now. Or actually, let's work on two different problems, okay? You guys ready? I'm going to give you an example problem. I'm going to give you 2 example problems, and then I'm going to tell you which ones to skip, all right? There's going to be a lot of problems I think that we should skip. Because to be honest, I really kind of want to go through an altitude with you, or what is it? It's center. I think we should just focus on the first 3. I think once you get a mastery of the first 3, the 4th one might come into play in the future. Not now, though. I think it's overloading you guys with a little bit too much, okay? So we're going to look at, this is 7-2, medians and altitudes of triangles. Medians and altitudes of triangles. And then the first thing that we're going to do is use the centroid theorem. So you guys just looked at the centroid theorem without even noticing it. And then here's an example. In triangle ABC, Q is the centroid and BE is equal to 9, find BQ and QE. So here's what the triangle looks like. It just looks roughly like this. Okay. I'm going to name these corners A, B, and C. Okay, and then here's what I'm going to do. I'm going to draw the medians on each side. So A and C, I'm going to find the midpoint and then draw the line here. We're going to call that line E. Then I'm going to draw from A to the other side, like the midpoint here on the other side. And that point over here will be D. D. And then from C to the other side, which is F, we draw that point over here. Boom. And the middle point is going to be called Q. By the way, 3 medians meeting at one point. What is that point called? What's another way of calling that point? The centroid. That's right, Natalie. You got it. The centroid, okay? But what if BE is equal to 9? If B is equal to 9, what is going to be BQ? That's the question.
BQ, B6.
How did you do that?
I just kind of thought that BQ was 2/3 of QE.
Natalie, you are wonderful, Natalie. Okay, so BQ, hold on. Let's first do this formally, okay? Meaning we got to show the line segment names. It's 2/3 times what, though, Natalie? Which line segment? BQ is 2/3 of what? B. Uh-huh. And then 2/3 times BE. What is BE? How long is BE? And I did this in your head, Natalie, okay? Like most of you guys did. But please, if you don't remember how to do things in your head, fractions in your head, you can do it step by step by doing this. 9, you can look at 9 as like 9 divided by 1. And then when you multiply fractions, you multiply the numerators and then you multiply the denominators. The numerator is 2 times 9 is 18. And then 3 times 1 is 3. It's 18 divided by 3. And if you remember your multiplication, that would just be 6. Okay? BQ is equal to 6. Any suggestions for the next one? QE. Uh-oh. What about QE?
Say 2/3 of 6.
Huh?
You say 2/3 of 6.
Is QE 2/3? Oh, 2/3 of 6? I guess you could look at it that way, but why don't you compare QE to the whole thing, BE? How does it compare?
1/3
1/3 of what?
of BE, I mean.
Yes, that's correct. So it's 1/3 times what? Times 9. And if you want to do that in your head, or just do that just without a calculator, it'd be 1/3 times 1, or 9 divided by 1. That'd be 9 over 3. And what would that get you?
3.
And if you want to make sure, BQ plus QE should equal what? Think about it. If this whole thing is 9, then BQ plus QE should equal what? Which is
9.
the whole, yeah. Or else it wouldn't make sense if this whole thing is equal to 9, but then this is 7 and this is 3. Then it won't be equal to 9. That doesn't make any sense. So that's a good way to make sure your math is correct. Make sure it equals the original length of the big line. Okay? All right? Okay, so let me see. It's 1:38. We have about 7 more minutes until I call it a day. Okay? Let's see. First, let's talk about which ones you are not going to do, right? So on your cover sheet, I don't know exactly what problems they are, okay? But are you ready for this, right? You guys didn't know, but we did example 1 and 2. Skip any problem that looks like example 3. Skip anything that has coordinate proofs. Okay, this section. And also, do not do anything with orthocenters or altitudes. That's example 4. Yes.
What if you already?
You did it already?
Yeah.
Oh, that's magnificent. Okay, well, I'll give you extra credit. Make sure at the top of your paper you say extra credit. Okay, so that way I can kind of double check. Oh yeah, I forgot these questions they didn't have to do. Okay, so I won't be testing you on this. I think this is a little bit too tough. I think I don't know. I really only want you to get like the stuff that we just went over. That stuff, if something, because if you learn all this stuff, you memorize it, and you don't remember any of it, what good is it, right? So I want you to memorize some of this, so that way some of it sticks. But if I give you too much, you're not going to remember any of it, right? So I don't know. That's my philosophy. Okay. So nothing with coordinate proofs in 7-1 and 7-2. Okay. No coordinate proofs. I think that's just too excessive. So you don't need to do that. If you're in honors, then I'll be like, different question. Then you can do it. And most people don't like that. So in this class, no. I think this is all you need right here. Okay. Let's see. PT. Oh, one more challenge question before I let you leave. Let me see if I can pause this really quick. Okay. Oh, whoops. Hold on. You guys aren't even supposed to see that part. Just. Okay, where's the centroid? P is the centroid. Hold on. How do you know these are medians that make the centroid? How do you know that all those lines are medians? Let's back up a second. How do you know? I'm going to laser point this now, okay? How do you know that KT is a median? What makes KT a median? What makes J to S a median? What makes R to L a median? What do you think, David?
Because they all come from vertices.
Huh?
Vertices.
They all come from vertices, all right? But we need one more requirement. It has to come from a corner, like you said. But what else? What do
They all
you-
intersect at point P.
They all have to. Oh, they do. Oh, but let's just say that we didn't know that it intersected yet.
Okay.
And I drew this only one at a time, like L to R. What does it do to this side? Yeah, Lena? It cuts the other side into 2 equal sides. Okay, so remember that. All right. Does it make a 90-degree angle though? If it does not, then it is a median. Okay. If it does, then we call it a perpendicular bisector. Okay. All right. Anyways, what if I give you this? PT is equal to 2. What is KP? This is your last challenge. How did you do that?
That's kind of half of it. P is like one third of KD.
Yeah, you're right. Man, that's it. All right, that's the end of class, guys. So, okay, so if you need to formalize it really quick, question. Go ahead and have a seat. Okay. You need to formalize it really quick. Okay. It's not even really quick though. I guess I should do it on a separate sheet of paper, huh? Yeah, maybe that makes sense. Let's see. They had a different way of doing it in the book, but I'll do it. Let's see. Let's do it in a way that makes sense to us, maybe. So, okay. So PT. How does PT compare to K? Whoops, I don't like this. I need a little bit closer. How does PT compare to the whole side? That whole side KT.
It's 1/3.
It's one. Yeah, you're right. It's 1/3 of KT, right? And you know PT is 2. So how do we solve for KT now? Yeah.
You multiply 1/3 by on both sides.
Oh, you don't multiply by 1/3, but how do you cancel out that 1/3?
3/1.
Yeah, you multiply by 3/1. And then if you multiply both sides by 3/1, what do you get? 3/1 times 2/1 is 6/1. Remember, if you multiply fractions, it's numerators divided by the denominators, okay? And you get 6/1 is equal to KT, right? We're not finished. I still need KP. Remember, I need KP. So how does KP relate to KT? If you look at how does KP relate to all of KT? You said that PT was 1/3 KT. What is KP then?
2/3.
Yeah, 2/3 times KT. So KP is equal to 2/3 times what?
6.
Yeah, you just solved for KT. And KP is equal to 2 over 3 times 6 over 1, which is 12 divided by 3. Sorry about that. There's all that work. And then what is 12 divided by 3? So I know, Natalie, you're able to eyeball it, but let's just say these numbers are a lot scarier in the future, right? A lot bigger. You still want to do it in a formal way, okay? But if you can eyeball like you did, it would save you some time too, okay? All right, guys, that's the end of class. So please remember, skip any problems that have to do with example 3 and 4, okay? We're going to avoid doing any problems with like 3 and 4. Examples 3. 7-2, okay? 7-2. All right, thank you guys so much for coming, okay? I appreciate it, guys. Yeah, no problem. And then this Thursday will be the last, like, 2 or 3 sections. We'll be done.
So I have a question about 7/1.
Yes.
36 to 39 problems. I'm wondering if those are the problems that are
I skipped. You can
Yeah.
skip them. Yes.
36 to 39, or it seems like I should do it. I couldn't really finish them yet, so.
You don't have to do 37 and 38. I'm so sorry about that.
Can I look at a cover sheet if you have a cover sheet on you, or should I ask Alina and see what?
I would maybe ask Alina because I don't have a cover sheet on me right now. I'm so sorry. Yeah, you don't have to do 37, 38. You could skip those. Hey, Alexis, go ahead and have a seat. No sign-ins today, so go ahead and have a seat for now. I know it's kind of messy. You guys, can you guys bring me the markers too?
It's 27 through 37 on 7/1.
Okay, so 27 through 37. The only one I don't, so 37. I don't want you to do 37.
That's it.
Is it odd or even or no?
All
27.
to 37.
Okay, and you don't have to do 37, and you don't have to do 36 either, okay? So yeah, hopefully that'll make it, but you have to do the rest. I think the rest is doable, okay? Thank you so much, guys. Yeah, just leave it right there. Thank you so much. All right. You guys have a great day. All right, we'll begin very shortly in a few minutes. See who else comes. It's really nice of you guys to come. Thank you. Is anybody else coming?
Toller has play practice, so.
He has what? Oh, play practice. Very nice. Hello, Meredith. You don't have to sign in. Just come in and have a seat.
No, I'm not going to be able to do it because I have to go to rehearsals in 10 minutes. So, like, what should I, like, review?
Okay. Well, if it helps, I'm going to try to tape what we do. So I'm going to try to send it to everybody else right now. So as you can kind of see on my screen right now, I just recorded the last section for the other class. So for anybody who couldn't make it to this class, I'm going to send them to.
Okay.
I think it's always a little bit better to be here, but if you're busy, it's fine.
Okay.
Why are you waiting for
Because I didn't want
You had a good weekend? What'd you do?
My grandparents are here, so I went to live in the station with them.
Oh, that's a nice place. Huh? Yeah, I really like the area. That's one of my favorite places to go. It's just really nice. They don't have the ice rink anymore.
No, it's only like seasonal, I guess. Just
Yeah.
during winter.
Okay. That's cool. Where are they from?
Michigan.
Oh wow! Like was it Midwest? I guess.
Yeah. So they're retired, so they took a road trip out here.
Oh, that's cute. That's cool. I wish I could kind of get to that point, but you can just kind of travel and do that, But then again, you're a little bit older too as well. I think one of the teachers here is retiring. So. Oh shit!
Here you go, Alexis. We have control. Why do you have a sparkling ball in your room just to read?
I don't know. I think there's a church here. They enjoy themselves.
Those sparkly balls are quite.
They're quite the fun, aren't they? They're quite the fun. Okay.
Close enough. I'm gonna throw it in that.
All right. Well, I will ask to refrain from playing now. I'm so sorry, guys. I know that you got that athletic itch to work out.
Yes.
Okay. Sorry, I'm just trying to stop the recording for this one, and then I'm gonna start a new one here. Everybody have a good weekend?
Yeah.
Busy? Oh, what'd you end up?
A big